As we have been saying repeatedly, we are interested here in the Earth system response, especially in terms of carbon cycle and biogeochemical cycles, because they also relate the biosphere to climate and other Earth system feedbacks. And we also have to worry about the other non-CO2 greenhouse gases as well. The Vostok Ice Core record, this combines various things here, going back to 800,000 years, gives us a very good sense of the methane variability in parts per billion by volume. That CO2 we have seen already several times, and the temperature record estimated from the deuterium isotope, which works almost the same as delta O18. And this shows what we have seen already before, that there is a very good phase relation with temperature leading by a few thousand years, which you cannot easily see in this record, but statistically significant lead lag relations do exist because these are forced by orbital forcings, which triggers the temperature response first by radiative perturbation, and then it triggers glaciation or deglaciation. Except we will see that it's not always that perfect a relation between orbital forcing or Milankovitch theory and glacial deglacial cycles. But you can see the amplitude shown here of 9 degrees centigrade. The warming in the last couple of hundred years has not been concatenated here, but that clearly shows that we are still kind of responding to the increase in CO2 and methane since the last glacial maximum. That's what we called committed warming and so on. So in the past, we know the amplitude relations between temperature response, CO2 response, and methane response. There is also the benthic foraminiferal response that is consistent. So these are away from the glacier into the ocean, and how the ocean temperature, ocean circulation, upwelling strength, primary production, etc. would have responded, because that's also part of the carbon cycle response, right? And this one shows pollen record from Tengahi Philippon, which in Greece, which is much noisier. Okay, so you have to do some statistical analysis, but you can see that when this is staying up here, this is staying up here with these dips, which are many more than the dips in here, and so on. So the vegetation response can be seasonally dominated, whereas these other things are slower. Especially the sequestration of ocean sediment signatures and CO2 response, methane response. So there are multiple time scales involved in there. But what is notable here is that these two green dots, which have the high phase of the insolation forcing at 65 north, which I already explained is critical because that latitude, the summer insolation, June 21, is the summer solstice, I hope, and that yes, so that tells you that it could be the period when the insolation determines whether you initiate a glaciation or you begin to end existing glacial period. But the magenta dot here, if you look at the temperature and CO2 and so on, that doesn't correspond to a termination. So these correspond to a termination, but not this one. So the Milankovitch cycle obviously is modulated by other things. We have to understand what are the other feedbacks that actually take the orbital forcing and extract a different time scale out of it. Okay, so the very close relationship in which millennial variations of CO2 resemble those of the Antarctic temperature records rather than the abrupt jumps of the records in the northern hemisphere. probably indicate that the Southern Ocean processes might be major players in this temperature CO2 relation that we keep looking at from Vostok. So considering it's in the Southern Hemisphere and the Northern Hemisphere records have a different time scale, abrupt jumps and more high frequency looking variability. There is some smoothing process, or there is some hemispheric asymmetry, or the ocean exchange, again the Southern Ocean being a special place, is controlling the global CO2 variability from glacial to interglacial, which is about 80 to 100 ppm. Okay, this is very important to understand, because that's going to determine how our carbon cycle feedback is going to work in the global warming phase as well, even though the time scales can be very different for the deglacial phase versus the glaciation phase. We are now in the deglaciation phase in some sense, especially with respect to Antarctica and Greenland. Okay, so at least at glacial interglacial time scales, then the Southern Ocean may be playing a more critical role. Lots of people spend a lot of time looking at the processes within the ocean which could have managed this ppm change in the ocean. There are several theories, as we will see. So we talked about the carbon cycle, but we didn't actually look at the profiles. Oxygen profile, this is good to relate these to the thermohaline circulation and the carbon cycle. So you expect oxygen to be high near the surface because there is exchange with the atmosphere, which has high oxygen, plus there is photosynthesis in most places in the ocean near the surface, where there are nutrients and light available. And you expect the Atlantic to have higher oxygen than the Pacific, because it has North Atlantic deep water formation, which then inundates the rest of the Atlantic as it flows south, and high oxygen is being taken down with the water, and this so-called oxygen minimum zone, where most of the species live and respire the organic matter produced, the food chain, is actually got much higher oxygen than the Pacific, because Pacific is not as ventilated with the atmosphere. It's older waters and it's depleted in oxygen. And you can see that the impact of deep water formation is that the oxygen increases slightly away from the oxygen minimum zone towards the bottom. So the high oxygen water is inundating the oceans all the way into the Pacific and increasing the oxygen a little bit. Corresponding to that, you have high utilization of nutrients. So photosynthesis utilizes it, and there is recycling and reformation of the nutrients, which remains fairly constant down to the bottom. This is nitrate in micromoles per kilogram. This is dissolved oxygen in milligrams per liter. And Pacific in this case is higher because it's accumulating the production from the surface and recycling nutrients and generating a pool of preformed nutrients. Obviously there is a CO2 signature that goes with it. CO2 is lower near the surface because photosynthesis is fixing the carbon. There is also outgassing and uptake by the ocean. And Pacific again has to have higher CO2 corresponding to the high accumulated production and respiration and reformation of the nutrients, and the Atlantic is lower. And the pH will be reverse of this, because this is more acidic, so pH will be lower. This is less acidic, so pH will be higher. Okay, those are the things we have to remember. And ocean has this special buffering ability. So CO2 dissolves, forms H2CO3, because CO2 dissolves easily in the water to form carbonic acid. The ocean doesn't get saturated because of alkalinity and so on. It can move the H2CO3 into H plus and HCO3 minus. So bicarbonate, which itself can move into carbonate and 2H plus. So it's gambling away the carbon dioxide that's dissolved and able to take up more than if it would get saturated. This is called the buffering ability. So with warming, we have to watch out for how this buffering ability of the ocean is changing. Okay, that shows up in terms of the pH, for example. As CO2 increases, you expect the pH to decrease. Ocean has maintained this pH of 8.01, 8.1 range over millions of years, but rapid increase in CO2 can make it acidic, which is what we call ocean acidification. And if CO2 increases too much, then the HCO3 begins to get increase, and then CO3, the carbonate ions can get used up. The reactions don't move. This is kind of equilibrium where you change things slowly. But if you rapidly increase CO2, then carbonate ions get used up for these reactions. So remember, these reactions can go in both directions. Okay, so that's when carbonate shell forming animals begin to have trouble. That's the main impact of ocean acidification, is that as you rapidly increase CO2 in the atmosphere, the buffering reactions get perturbed in a way that carbonate ions get used up, and that affects calcium carbonate forming shells and silica shells as well, corals, coccolithophores, and other various kind of forams, etc., which form calcium carbonate shells. Okay, so that's the brief introduction to the ocean carbon cycle, and to highlight the point that the relation between CO2 and temperature during glacial deglacial cycles seems to be heavily controlled from the Antarctic side, just based on the observations we have.